Welcome back to the second lecture on functions. In this fourth segment, we're going to study ways of creating new functions from existing ones. So for example, let f1 and f2 be two functions, where the domain is anything, the set D, but the codomain must be the set of real numbers. Then we can define a new function called f1 plus f2, which is defined as follows for all of the elements x in the domain D. The value of the new function applied to x is equal to the value of the first function applied to x plus the value of the second function applied to x. So this is just the addition of two functions to create a new function. Now similarly, starting with two functions f1 and f2, we can create a new one by multiplying them. So this is a new function that, when applied to x, returns the value of the first function multiplied by the value of the second function, both applied to x. So these are two different ways of creating new functions by addition or multiplication of two existing functions. Now, a more interesting way of creating functions, new functions, is by composition. So now we're going to start with two functions. The first one, we're going to call it G. It goes from domain A to codomain B. And the second function goes from domain B to codomain C. Notice the domains are not random. G goes from A to B, and F goes from B to C. And that is important because now we're going to compose these two functions, F and G, in this order, which we denote by this circle notation here. And the way this function f compose G is defined is as follows. When you apply it to x, what you need to do is you need to compute f of G of x. In other words, the order matters here. When you compose f with G, the first thing you need to do is you need to apply G to x, and whatever result you get, you apply f to that. And as a consequence, it must be the case that the codomain of G is the same as the domain of f, which is the case in the assumption B satisfies this condition. And as a consequence, notice that the composition of the functions G and f in the order f, so-called G, is a function that goes from A directly to C. And that's because first you apply the function G to x, so G takes you from A to B, and then you apply f to that result, which takes you from B to C. So in conclusion, the composition of the two functions takes you directly from A to C. To get more comfortable with these new operations on functions, let's consider an example. Let's take the function f from the integers to the integers defined as f of n equals n plus 1. And let the function g from the same domain to the same codomain be defined as g of n equals n squared. I'm going to write down a series of questions first. Then we'll discuss the answers. So, is f an injective function? Is it a surjective function? How about G? Is it injective? Is it surjective? Now, the second kind of problem using the same example will ask you to define the function the function h, which is a new function computed by combining the functions f and g in different ways. So in the first part, h is the addition of f and g. The second part, h is the product of f and g. In the third part, f is the composition of f and g in this order. In the fourth part, h is the composition of g and f in this order. So in all four cases, I need you to define the function h completely. Then I want you to tell me what is the inverse of f if it has one. I also want you to compute or tell me what the function f composed with the inverse of f is. And finally, what is the function inverse of f composed with f? Please stop the video and answer these questions to the best of your ability and come back when you're done. Okay, let's check our answers. Is f injective or one-to-one? Remember, what that means is if you take two different integers and you add 1 to them, can you ever end up with the same answer? And the answer is no. So definitely f is injective or one-to-one. Now, to determine if f is surjective, we need to find an integer n such that you can never find a pre-image for n. Well, that can happen because for any integer n, you can always find another integer such that that integer plus 1 is equal to n. In fact, the pre-image of n is just the integer, the next smallest integer. So f is definitely surjective. Therefore, because it's injective and surjective, or it's one-to-one and onto, it's definitely bijective, and therefore it has an inverse, so we'll be able to answer this question. Now let's turn our attention to G. Is G injective? Is it possible to find two different values of n such that when you square them you get the same answer? And the answer is yes. Take 1 and minus 1, or 2 and minus 2. You're going to get the same square number. So G is not one-to-one, is not injective. Is it surjective? Well, no, because it's possible to find an integer, for example 3, that has no pre-image by G. There's no square number that's equal to 3, at least when the numbers are integers. You could also have chosen a negative number. There are no integer that when you square it, you get minus 2. So G is neither injective nor surjective. Now, let's define H when it's the addition of f and g. The first thing to remember, and I'm only going to say it once here, is that to define a function, you must define its domain and its codomain. In all cases here, I'm going to write it every time I'm going to say it once. The domain is z, the codomain is z, because of the definitions of f and g. Now, the second half of the definition is how to compute the image of n through h. Well, h of n is f of n plus g of n. So it's n squared plus n plus 1. F of n plus g of n is obviously the same as g of n plus f of n. In the second example, we need to compute the product of f of n and g of n. So h of n is equal to n squared times n plus 1. In the third case, we must compute g of n first, and then apply f to the result. So g of n is n squared, add 1 to that, so h of n is n squared plus 1. Finally, in the fourth example, we must first apply f, and then apply g to the result. So given n, f of n is n plus 1, then we feed n plus 1 to the g function, which will square it. In other words, h of n is n plus 1 squared. Now we already know that f has an inverse. What is the inverse of f minus 1? Well, the answer is f minus 1 of n is a function from z to z that returns n minus 1. So the inverse of adding 1 is subtracting 1. Now what is f composed with this function, f of n minus 1? Well, of course, it's the identity function. So h of n is equal to n. First you subtract 1, then you add 1, you get n back. And you should realize that every time you compose a function with its inverse, whether in this order or that order, you get the identity function. So also in this case, h is the identity function. In other words, the same function as here.